Hello. This short video is going to be introducing the concept of the mole. So the mole in chemistry is not talking about the animal, it's talking about something that's more related to the word molecule. If you look back in the origins of the words, it has something to do with a mass of something. Okay? So a mole is like a quantity of something, and we're going to describe what that quantity means in this little introduction. If you haven't already, there are some good YouTube videos introducing the mole as well. I have posted one on the playlist. I recommend that you watch that. So the way this started is that chemists were looking at things like individual atoms, which were very small. And if you look at the periodic table, there are masses that are written underneath a lot of different things. For instance, carbon has a mass of 12 underneath it. 12.01 technically on the periodic table, which is the average atomic mass, but the most common isotope of carbon is carbon-12. All right, that mass of carbon, as we've talked about it in the past, is related to the protons and neutrons in carbon. Carbon has 6 protons and 6 neutrons if it's carbon-12. All right, and so the mass of a carbon-12 atom, an individual atom, is 12 atomic mass units. An atomic mass unit is equal to the mass of a proton or a neutron. Again, carbon having 6 protons and 6 neutrons has a mass of 12 atomic mass units. What chemists wanted to do is find a way to talk about masses of things in larger quantities and still use the masses on the periodic table, which were based on protons and neutrons. To do that, they needed to come up with a conversion factor. The conversion factor is the number of atoms that would be necessary to give us the mass that we had on the periodic table, or in this case, it's all based on carbon-12. Which is the most common isotope of carbon. And so we say that a mole of something is the number of carbon atoms in 12 grams of carbon-12. All right, carbon-12 being the isotope of carbon that has a mass of 12, 6 protons and 6 neutrons. I'll get into discussing this a little bit more clearly here in a second, but we call this number Avogadro's number as well, and it's equal to 6.02 times 10 to the 23rd. Of anything. And 6.02 times 10 to the 23rd is that magic number. If you have 6.02 times 10 to the 23rd carbon atoms, it's 12 grams. All right, so the mass matches up with the mass on the periodic table, which is based on protons and neutrons. And this is actually true for anything. If you look at oxygen, the mass is 16. So if you have a mole of oxygen atoms that is 6.02 times 10 to the 23rd oxygen atoms, it has a mass of 16 grams. That is the convenience or the utility of using this number 6.02 times 10 to the 23rd. If we have that many atoms of something, it gives us the same mass that is listed on the periodic table. I will do a whole lesson later on what is called the molar mass of different things. So 6.02 times 10 to the 23rd is a really big number. You can see I have it written out here in its long form. All right, it's actually almost inconceivably large. The symbol that we use to represent the mole is just MOL without the E. I kind of laugh at this because I think in terms of chemistry abbreviations, this is hardly an abbreviation at all. MOLE versus MOL, but it is a little bit shorter, so we use the symbol MOL to represent moles in chemistry. In class, I showed students a bunch of different baggies that had a mole of some different substances. What we saw is that a baggie that had a mole of sugar in it looked like it was larger or more full than a baggie that had a mole of salt in it, all right, which was actually larger also than a mole of water. And so the question is, why is it that these baggies, which contain moles of different substances, why are they different sizes? Well, different atoms or different molecules are different sizes. So if we have a mole of sugar molecules are larger than salt molecules, so a mole of sugar molecules is going to be larger than a mole of salt molecules. To think about this in a different way, if you had a mole of marbles versus a mole of basketballs, the mole of basketballs is going to be a larger volume, all right? Because remember, a mole is 6.02 times 10 to the 23rd of something, 602 sextillion. So 602 sextillion basketballs is going to be larger than 602 sextillion marbles. This is also true for the atom. So if you have larger atoms or larger molecules and you have a mole of them, the larger the molecule, the larger the molar volume of it would be. A way to think about moles is just as a counting or a grouping number. So if we think about a dozen eggs, that's 12 eggs. If we have a mole of eggs, it's 6.02 times 10 to the 23rd eggs. And what we do is we use this as a conversion factor. 1 mole of something equals 6.02 times 10 to the 23rd of that thing. So going down, to do an example of this sort of problem, it says how many moles of boron do we have if there are 4.53 times 10 to the 34th atoms? So what we start with here, we're going to do a conversion problem. All of these mole problems are sort of like conversion problems. And we start with 4.53 times 10 to the 34th. And I use that E34 here. And then I want my label here. It's atoms, and I like to put the substance in there as well. So atoms of boron. We need to get out of atoms of boron and into moles of boron. So I'm going to have atoms of boron down on the bottom, so it will cancel out, atoms of boron. And then I'm going to have moles of boron on the top, so that we will get into that unit. So then atoms will end up canceling out. Now, the question I encourage students to ask themselves are, based on what we've said before, are there 6.02 times 10 to the 23rd moles in one atom? Or are there 6.02 times 10 to the 23rd atoms in 1 mole? Hopefully out of those two, one of them sounded better. It's 6.02 times 10 to the 23rd, or E23, atoms in 1 mole. As far as the significant figures go, because we need to consider significant figures, that first number, 4.53 times 10 to the negative 30, times 10 to the 34th, that had 3 sig figs. 6.02 times 10 to the 23rd also has 3 sig figs. 1 mole, this is a perfect number 1. The 6.02 is rounded, but that 1 mole is the perfect number 1. So we're not going to count that 1 mole as having 1 sig fig. Really, the 1 mole is infinitely many sig figs. So we kind of ignore that when we're counting the sig figs. So we look at the 4.53 and the 6.02. Both of those are 3 sig figs, so our answer should have 3 sig figs. If you put this into your calculator, you should get 7.52 times 10 to the 10th, 7.52 times 10 to the 10th. And then the units on that are moles of boron. For the second problem, we are given a number of moles of titanium, and it's asking how many atoms do you have. So this one's a little bit different because we're starting with moles instead of starting with atoms. So we start off again with the number that they've given us in the problem, 32.00 moles of titanium. And it's asking us for atoms of titanium. So what we have to do is we have to cancel out moles of titanium and get it into atoms of titanium. You have to think about where the 6.02 times 10 to the 23rd goes again. Is it 6.02 times 10 to the 23rd atoms in 1 mole, or is it 6.02 times 10 to the 23rd moles in 1 atom? Again, you should come up with 6.02 times 10 to the 23rd atoms in 1 mole. All right, so moles cancels out. We get into atoms. You put that in your calculator, and you should get, this should have 3 significant figures because 32.00 is 4, 6.02 is 3, and then that 1 is the infinitely many. It's that perfect 1. And so we've got 3 sig figs in our answer, 1.93 times 10 to the 25th. And the units on that are atoms of Ti. I'm going to go through 2 more examples of these. So this one says how many atoms of tungsten are in 1.261 moles of tungsten. So we start what's given in the problem, 1.261 moles of tungsten, moles of W is tungsten, comes from wolfram, which was the old name for tungsten. And then we need to cancel out moles of W and get into atoms of W. So then we know that there are 6.02 times 10 to the 23rd atoms of W in 1 mole. Take 12.61, which has 4 sig figs, and multiply it by 6.02, which has 3 sig figs, and we should get an answer with 3 sig figs. When you calculate that, you should hopefully get 7.59 times 10 to the 23rd. And then the units are atoms of W. For the last problem here, it says you have 42 atoms of potassium. How many moles do you have? So 42, it should strike you, that's not a lot of atoms, so we're going to get a pretty small number here. 42 atoms of K. By the way, you might notice I've been stacking the units in the last problems, and I didn't do that in this one. It doesn't really matter. It's more just to try and conserve space that I normally stack them. I just didn't here because I wasn't thinking about it, but it doesn't matter whether you write them stacked like I had in the previous problems or whether you write it out long ways like I did here. All right, so we want to cancel out atoms of K to get moles of K. All right, and so the 6.02 times 10 to the 23rd goes in the bottom in this case. Oops, 6.02 times 10 to the 23rd. So 6.02 E23 in 1 mole. We've got 2 sig figs in the, from the 42, 3 sig figs from the 6.02 times 10 to the 23rd, so we should have 2 sig figs in our answer. If you find that and round it correctly, you should get 7.0 times 10 to the negative 23rd moles of K. In this video, I will not be going through the remaining examples from your homework. However, you can find the PDF version of the key on the internet, and the problems are exactly the same as these. There are really only 2 types, the types where you start with atoms and the types where you start with moles, but they all set up exactly the same. So hopefully by looking at the PDF key, you can kind of figure them out. And if you can't figure them out, you can always come in and ask.